Okay, so this was a pretty cool lab today because using measurements in a lab, we were able to estimate the size of atoms. So in this lab, what we were doing was we were taking a oil drop inside of this little paperclip thing. So the paperclip thing was like this. And we pick up an oil drop, which takes on the shape of approximately a sphere. Um, now, so this is a little sphere here. And the formula for the volume of a sphere is 4/3 pi r cubed. I'm just going to get that ready. And so I measured the radius of this tiny sphere, as best I could. And we had about 0.10 centimeters. Again, I went to the hundredths place because we were using a meter stick that measured to the tenths, and I have centimeters down because we use metric units. So we're continuing the concepts we learned in Unit 1. So what I did is I put this oil drop in a tray filled with water and sprinkled with these little tiny this tiny powder. And when I put the drop in there, this sphere spreads out as far as possible into this layer that is about 1 molecule thick. And if you want to know what that molecule was, the oil we were using was this oleic acid. So this molecule, we can assume that it's kind of being flipped. So it's going up and down vertically there in this water. And then if I was able to measure the radius of this cylinder here, I got 16.75 centimeters for this radius. So this is the radius of the cylinder. And the volume of the cylinder is pi r squared. It's the surface area of this circle times the height. Now, if we put this drop and it's spread out in water, making this cylinder, let's do this. Let's assume that this volume equals this volume. So volume 1 equals volume 2. Okay, now for volume 1, 4/3 pi r cubed. If we substitute the radius of that sphere, which was 0.1 centimeters, we get 4.2 times 10 to the negative third centimeters cubed. So that would be the volume of this sphere again, this little sphere of oil. Now, once I put that in the water, if all of this went in the water and it spread out and we measured it, well, this volume should equal this volume. So that means that 4.2 times 10 to the negative third centimeters cubed should equal pi r squared h. Now that pi is there. Now this r squared would be the radius of this cylinder. So now we're looking at 16.75 centimeters squared, and then times the h. Now my goal here for now is to calculate the height of this molecule right here, this height h. So let's divide both sides by pi and by 16.75 squared. So we do that and we get h equal to 4.8 times 10 to the negative 6 centimeters. Now again, we're back at a distance here. We got rid of our cubes and our squares because we divided centimeters cubed by centimeters squared. And again, I have two sig figs here because the least in my value up here was 2. Okay, now, if you look back to the lab, this molecule is 21 atoms long. So if we could now divide the height of that by 21, we could get the size or the length of about 1 atom. So if the height of this is all 4.8 times 10 to the negative 6, we divide that by 21, and 1 atom should then be about 2.3 times 10 to the negative 7th centimeters. Now notice when we are looking at the scale of the universe, those values were all in meters. This is in centimeters. So let's again practice something from Unit 1 and remember that there are 100 centimeters in 1 meter. So I'm actually going to do this the unit conversion way and just say that 1 meter is equal to 100 centimeters. Let's get my units to cancel. And that just means that we have 2.3 times 10 to the negative ninth meters as the approximate size of this atom. You can now compare this to some of the values we looked at in the scale of the universe simulation and just see how maybe close we are. And, it's pretty good. We're actually in the ballpark. I think, we're at that negative ninth scale. So we really got there, that we were able to estimate the size of one of the atoms that made up this molecule. So I hope this little video helped and helped clarify and walk you through the calculations one more time.